Rightio, let's learn about energy levels in atomic physics. Here is a representation of the energy levels for hydrogen. This level here, basically it's a way of representing what Bohr's model of the electrons. You have your nucleus here, and then the electrons can only sit at certain energy levels that are characteristic for that element. And every element in the periodic table has its own set of energy levels because they all have different nucleuses. And what's referred to as the ground state is where the electrons would sit if there was no excess energy in the atom. And then above the ground state you have these excited states, or these energy levels, which are possible if the electrons in the ground state gain energy. They can jump up. But the electrons cannot sit between these energy levels, they have to sit on these energy levels. And the energy levels have values. Now in this case, it's written in EVs, and the negative indicates that energy is required to go up there, and energy is released when it goes there, down there. Could also be written in joules, because joules and electron volts are both a measure of energy. And you'll sometimes see some diagrams that have it around the other way around, where the ground state is regarded as 0, and then you have the energy of ionization up here, because if any electron has gains from the ground state greater than 13.6 EVs of energy, it actually becomes free of the attraction of the nucleus, and therefore the nucleus becomes ionized, or the atom becomes ionized. And so there's no strict convention, and I think some of the questions I give you may have different versions. You just got to recognize what the ground state is and what you're actually given. Now where's my pen gone? Right, this is another representation of it, again having the nucleus in the middle and just showing the energy levels. And in this case I think they're showing hydrogen, yep. And so this is the spectrum for hydrogen. And where do these lines come from? Well, this is the ground state. No, this is the ground state here. Or is it here? No, it's here, I think, yep. And when the electrons gain energy and jump up here, they then drop back into the ground state and give off the photons. And this corresponds to the red photon. Jumping back from here to here corresponds to the, what is it, blue-green they reckon. And then jumping from here and here give you the violet ones. Just a different representation. Now we're simplifying it as well, because there's all these other transitions that can occur, and they can also give off photons, or will give off photons. And they're actually given names because they've been studied so much and people want to refer to them specifically. So they get some of the series of transitions are given their own names. Now let's have a look at what we can actually do with or how we get atoms excited. And there's a couple of ways that we can get them excited. So we might actually get a whiteboard. Let's go with a black screen. Here we are, and let's draw some things. Right, so let's imagine there's our ground state and there's our electron, and here's another atom, same atom, and there's our electron. And really for us there's two ways that we can get these guys excited. And let's draw in, oh that's a bit shaky, let's draw in some more energy levels. Okay, and one way is by bombardment by electrons, and the other is by absorption of photons. And there's a subtle difference between the two. With the electron, it's a particle. and so it has kinetic energy. The photon isn't a particle, but it has energy, and that energy is equal to hf. Okay, but it's a quantum. I missed the N there. It's a quantum in that the photon can only give all or none of its energy. Bit slopey, everything's a bit slopey today. Whereas the particle, the electron, can give none, some, or all of its energy. And the consequences of that are subtly different. So if we bombard an atom with electrons, let's imagine we're sending in some electrons, and these electrons may all have the same energy or a different energy. There's a number of things that can happen. The electrons can just whiz straight through, okay, and so they don't lose any energy. They can undergo an elastic collision, alright, where they interact with the electric fields and magnetic fields, and they go off, but they still don't lose any energy. Or they collide and get scattered, and the kinetic energy is reduced because they've given some kinetic energy to the atom's electron. And these guys are your scattered electrons, which can have variable energy depending on the type of collision that occurs. And so this electron needs to gain exactly the right amount of energy to go and sit up here. And so lots of collisions may occur, and the electrons may gain energy, but they then lose it. Basically what happens is the atom's just getting hotter, because these electrons are just gaining energy, but they're not actually gaining energy sufficient to go up to a new energy level. Now with the photons, however, if we bombard something with a series of photons, the photons can either go straight through. Now they have to have, if this energy jump is E2 to 1, let's say, this photon must have exactly that amount of energy. And if it is, it goes in, gets absorbed, and the electron jumps up. And the photon no longer exists because the energy has been transferred to the energy of the photon has been transferred to the electron. And so in this situation you can have ones that pass through. Now if this E does not equal E2 minus 1, so you can have a whole lot of photons coming in that all have different energies, but it's only the photons that correspond to the energy required for the transition that are absorbed. All the others just go straight through and aren't absorbed. So there's a subtle difference here. Here you can bombard atoms with a whole lot of electron energies and things will happen. Here you've got to have it exactly the right frequency. Enough of that, let's have a look at a couple of examples, I think. Let's see, I need this. Where's my screen gone? On the black screen. Oh, let's get rid of the writing then. Yeah, I could have drawn it there. So let's walk our way through a couple of examples. So in this case we've got an atom and it's being bombarded by electrons. And so atoms are bombarded by electrons. The bombarding electrons give up some or all of their energy to the electrons of the atom and are therefore themselves scattered with reduced energy. In this case we've got a beam of electrons with an energy of 8 electron volts, and we're not told what element it is, but we're given a diagram, and we want to calculate the energies of the scattered electrons and the possible energies of the photons emitted. So this should appear. There's our energy levels. There's our bombarding electrons with 8 electron volts, and these are our energy levels here. So first of all, the scattered electrons, we get a range. We can get the ones that just have an elastic collision, basically nothing happens, and they bounce off and they have 8 electron volts. Then we get the ones that are caused to transition from here to here. Okay, and that means that they must lose that amount of energy, and therefore they are scattered at 2.7. So this little jump here corresponds to 5.3 electron volts. Now the next ones that can be scattered are the ones that cause a transition from here to here, and so this corresponds to this, and they are only left with 0.1 electron volts of energy, and they would correspond to, from there to there, 7.9 EVs. So we could end up with electrons sitting here and here, plus these scattered possibilities. Now this one's not possible, the next jump up is not possible, because the bombarding electrons do not have a sufficient energy. So they're the energies of the scattered electrons are 8, 2.7 and 0.1 electron volts. Now what about the photons that can be emitted? Well, the photons can come from these two electron possibilities. So when this jumps back down like that, it will emit a photon, and the photon will be 5.1 EVs. When this one jumps back, you'll get 7.9 EVs, and there is the possible jump. You can also jump back in a two-stage process, and this one here would be 2.6 EVs. So a photon would be given off like that. Let's go back, and a photon will be given off from there. So we actually have 3 possible photons emitted. Hope that makes sense. Let's move on to the next one, where we're bombarding with photons. Now when atoms are bombarded with photons, the interaction means that only if the photon can be completely absorbed does anything happen. What we're saying is that the photon energy must correspond exactly to the difference between the ground state and possible excited state. Alternatively, the photon may ionize the atom, as we mentioned before. This is mercury, okay, and in this case we're given our energies in joules, just to be a little bit different, and we're asked a couple of questions. What energy photons may be absorbed by atoms of mercury, assuming the existence of only the levels shown? What energy photon is required to cause ionization of the atom? If the atom is ionized, what is the maximum frequency of photon that will then be emitted, and how many lines will appear in the emission spectrum of this atom, assuming only these levels? Let's have a look at the answers. So in terms of the photons that can be absorbed, we really need our diagram back. Basically they have done, let's go back here, they do the first jump from there to there, and so this would be subtract this number from this number from this number, gives you the amount of energy required. And they've been a little bit tricky in that they've taken the times by 10 to the minus 19 outside of the brackets. So there's one jump, there's the next jump up to the next energy level, and then to ionization. And that would be the photon absorbed. Now if there's any photons with greater than that energy, they could also be absorbed, because the electron would just have excess energy and be moving faster. Ionizing would therefore be caused at this energy level, and if we go back to the diagram, this is effectively our ionization energy, or higher. Now when the electrons are falling back from infinity, so unattached to the atom, jumping back into the ground state, it's going to give off this amount of energy in joules, and so we can then using E equals hf calculate the calculate the energy and then convert the energy to, that would give us the frequency. Okay, so we've rearranged this to work out F. So there's our energy in joules, there's Planck's constant, and there's our frequency in hertz. And you might be asked where that sits, so you'd look at your electromagnetic spectrum and you'd see it's in the ultraviolet range. Now, in terms of the possible transitions back, these are all the possibles, and notice that they've grouped them a little bit because there's again there's some groups, and it helps to be systematic. And so there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 possible photon energies that can be given off. And now you should be able to do all these questions. See ya. Oh, I forgot to say, next video we're doing lasers. Now I can say, see ya.